Hello everyone. In this video, I want to show you something simple and I want to basically emphasize the importance of trigonometry because you might say, why do I learn all these sines and cosines and tangent and show these identities and so on? Do they have any real application in real life? Well, if you are an engineer, and especially in something like robotics, you are dealing with those sines and cosines all the time. So, by going through your courses, you know that they have a lot of applications. But if you're not necessarily in the field of engineering, you might say, where do I use these sines and cosines? So, here I'm trying to motivate you. And the two pictures and the formulas are coming from this website. Okay, so I could have made them myself, but I decided to take them from this website. So all the credit goes to those people, and they are really good pictures. So about 900 years ago, a polymath called Biruni, that was really knowledgeable about all science of his time. He was a Persian, basically astronomer, and so many other things. He basically estimated the radius of the Earth to be about 6,339 to 6,340 kilometers, and it was only 1% away from what we know today. So imagine 900 years ago, within 1% of error, you estimate the radius of the Earth without any satellite, any device, anything. And all he did was trigonometry. So let me show you how you can do it and see the genius of this person. So what did he do? So he considered some mount. Okay, he went close to some mount, which they say it was in today's days Pakistan, and he had a device which is called the Osterlob, and he could measure angles with relatively accurate measurement within 2 decimals of a degree, so like 30.56 degrees or so. So he had a device for measuring angles pretty accurate, and that is another genius thing that they invented back then. So he basically pointed toward the tip of the mount, and then he measured the angle at a location that he was standing, and he came up with this angle theta. So he measured it, then he moved the distance d forward toward the mount and try to again measure the angle from his position to the tip of the mountain. So he measured angle theta 2, and then using theta 1, theta 2, and this distance d that he knew how much he traveled, first he estimated the height of a mountain. And then using that, he estimated the radius of the Earth. So first, how did he measure the height of the mountain? He used this formula that h equals d tangent of theta 1 tangent of theta 2 over the subtraction of the two tangents. And clearly you see the trigonometry function here, right? You see the tangent function. Now you might say, where does that come from, huh? So if I call this distance from the second position to the bottom of the hill or mountain, it should be actually a relatively tall mountain to be used for the Earth. So if I call this distance s, you can clearly see that here we are dealing with two right triangles, correct? One of them is this one, and the other one is this one here. So if I look at this smaller one, I can see that basically h over s equals tangent of theta 2. So from here, I can say s equals h over tangent of theta 2. If I look at the bigger one, I can say that h over d plus s equals tangent of theta 1. So from here, I can say that d plus s equals h over tangent of theta 1. And all you need is to subtract these two. So just go ahead and subtract them. If you do that, the s would go away. You're down with the d, and on the other side, you have h times 1 over tangent of theta 1 minus 1 over tangent of theta 2. And if you take a common denominator, clearly this is going to be h times tangent of theta 2 minus tangent of theta 1 divided by the product. And now all you need to do is to basically solve h as a function of d and this. So what you need is to multiply this by d and divide it by this one, and that will exactly give you this. So all I need is to measure theta 1, 2, and the distance traveled d, and that will give me the height of the mountain. Now that you have the height of the mountain, how would you use it to measure the radius of the earth? So now he climbed to the top of the mountain, and again, using his angle measuring device, the astrolabe, he could measure this angle alpha, which we call it the angle of depression. And this is the angle between basically a horizontal plane parallel to the top of, not parallel to, I mean perpendicular to the mountain, right? Or basically if he stood on the top of the mountain and he was looking, basically this is straight from his eyes, straight out of his eyes. And this is where he could not see above this point. So this point is the point beyond which you cannot see because of the radius of the earth. So you guess right, that is the horizon. So the angle between his eyes and the horizon, and the line that is going straight perpendicular to his body, the angle here called the angle of depression. And by measuring that one, now with having that alpha and having h, the height of the mountain, now you can measure the radius of the earth r. How? So here, if you take a look, you know that since this line is a line tangent to the surface of the earth, it is perpendicular to this radial line here. And so here you're dealing with the right triangle again. This distance is r, this distance is r plus h, because r is from center to the bottom of the mountain and h is above that, so it's r plus h. And you can clearly see that r here adjacent to alpha is equal to the hypotenuse, which is r plus h, times cosine of alpha. Now the question is, why is this angle also alpha? If this angle is what I called alpha, why is this other angle alpha? And that is extremely simple from triangles again. Why is that? Because here, some of this angle and this one here is 90 degrees. Remember, this is a perpendicular. And also, some of this angle here, whatever you want to call it, let's call it beta. So alpha plus beta is 90 degrees. And also beta plus this angle, whatever it is, should also be 90 degrees. Why? Because they form a triangle and it is a right triangle. So clearly you see that this angle should also be alpha. And now, as I said, in this right triangle, r equals r plus h cosine alpha. And if you solve for r from here, r is going to be h cosine alpha over 1 minus cosine alpha. And now you see the trigonometry function cosine is showing itself. So if you have measurement of alpha, and if you have the measurement of the height of the mountain, which you got it just from this top formula here, guess what? You are going to be able to measure the radius of the earth. And he did it within 1% of the actual number that we know today, 900 years ago. So hopefully now when somebody says, hey, where would you use sine and cosine? Say, okay, if you want, you can go ahead and measure these numbers, huh? And then maybe you won't say that the earth is flat, huh? Because 900 years ago, somebody measured its radius. Okay, so hopefully this was useful to you. I'll see you in the next video.